Today we're going to carry on where we left off and find a faster alternative to calculate the derivative. Last week we learned that the derivative can be calculated from first principle, and it is f prime of x is equal to the limit as h approaches to 0, f of x plus h minus f of x all over h. Though the first principle is the formal definition of the derivative, it is very tedious to calculate, and for that reason nobody actually uses it. As such, today we'll be discovering our first method of speeding up the calculation of the derivative, the power rule. As we know from our last video, the derivative is just the instantaneous rate of change at a given point, and the first principle is just an altered version of the slope formula. The only difference between the two is that the derivative is over a very small change in x, which is why we add the limit as h approaches to 0. So let's try and derive a simpler rule to calculate the derivative of all positive polynomial functions. To keep it simple, let's define a function f of x equals x to the n. Using the first principle, we can set up the standard way to calculate the derivative. This would be the derivative of f of x is equal to the limit as h approaches to 0, x plus h all to the n minus x to the n, all of this over h. From here, we have two options. Evaluate the numerator and cancel out the h terms to calculate the derivative using first principle, or use the binomial theorem to simplify this function into a general rule. As a refresher for those who may not remember the binomial theorem, this is an interesting principle which allows us to expand any binomial. A binomial is just x plus y to the power of some integer. For example, x plus y to the power of 3 is a binomial. You may be asking yourself, why don't you just expand these two terms by multiplying x plus y 3 times itself? And yes, you would be right, but you could see that doing this multiplication gets very tedious if we get larger powers, such as 10 or even 100. So to save us some time, we can use the binomial theorem, which states that the expanded binomial is equal to the sum of n choose k times x to the n minus k times y to the k, where k equals 0 and n equals to the highest power of your binomial. You may be wondering, what is this n choose k business? Well, this is a simple way of representing a factorial expression. So, n choose k just means n factorial divided by k factorial multiplied by n minus k factorial. Though both of these formulas are a little bit complicated, take some time to familiarize yourself with it, as it's quite important for this video. So bringing ourselves back to our original problem, the derivative of x to the n has a binomial term in the numerator. As such, we can use the binomial theorem to simplify this term. As such, it will be n choose 0, which is 1, times x to the n times h to the 0, plus n choose 1 times x to the n minus 1 times h, and so on. We keep doing these n choose 1 all the way till we get n choose n. So once we have our expanded binomial, we can look to simplify. So we have an x to the n at the front of our binomial, and we also subtract an x to the n at the end of our entire term, so we can cancel those two out. Now we can look at all of our terms, and every single term has an h in it. So we can divide all of our terms by h, which gets rid of the h in the denominator and gets rid of one of the h's in every single term in the numerator. And this gives us the following: n choose 1 times x to the n minus 1 plus n choose 2 times n to the n minus 2 times h, and so on. Now we can evaluate our limit by substituting 0 into all h terms, and we're left with the derivative of our polynomial x to the n is equal to n choose 1 times x to the n minus 1. So let's evaluate the n choose 1 term, which is n factorial over 1 factorial minus n minus 1 factorial. We know that 1 factorial is 1, and n factorial over n minus 1 factorial is equal to n, for the same reason that 3 factorial over 2 factorial is equal to 3. Therefore, our n choose 1 term is just equal to n, so the derivative of x to the n is equal to n times x to the power of n minus 1. And this is the power rule, or a method to calculate the derivative of polynomials much faster than the first principle. So that was a bit much, but feel free to rewatch this proof if you truly want to understand the derivation of the power rule. But for now, let's move on to some sample problems as well as a graphical verification. Let's take the function f of x equals x squared and use the power rule to determine the derivative of this function. So the power rule states that the derivative, which is f of x prime, is equal to n times x to the power of n minus 1, where n is the exponent of your x term. So the derivative of x squared is 2 times x to the 2 minus 1, which is just 2x. That was simple. It's pretty much a one-step solution, which is much quicker than using the first principle. But is it right? Well, let's use a graphical method to check our derivative function. So let's plot f of x equals x squared, and remember that the derivative is just the slope of the tangent line at a certain x-coordinate on f of x. So the derivative at x equals 2 is the slope of the tangent line at x equals 2. Graphically, we can use the rise over run formula to calculate the slope of the tangent line and find that at x equals 2, the slope of the tangent line is 4. Verifying this with our derivative function, we can see that the derivative at x equals 2 is equal to 2 times 2, which is also 4. You can graphically verify the slope of the tangent line at any point and check whether or not our derivative function is correct. But if you trust the power rule, this is a method that can quickly calculate the slope of the tangent line or the derivative of any given x-coordinate of a polynomial. So now let's move to some more difficult sample problem. Let's calculate the derivative of 3x cubed minus 4x squared plus 8x plus 10 at x equals 4. If we were to use the first principle, this would take us an eternity, so let's use the power rule. Let's recall that the power rule is equal to n times x to the power of n minus 1, and since our function has 3x term, we have to use the power rule 3 times. As such, the derivative of our function is 3 times x to the power of 3 minus 1 minus 4 times 2 times x to the power of 2 minus 1 plus 8 times 1 times x to the power of 1 minus 1 plus 0. And we have 0 at the end of our derivative, as the derivative of a constant is 0, and we'll get into that in our next video. But after simplification, we can determine that our derivative of our function is equal to 9x squared minus 8x plus 8. Now we substitute 4 into our derivative function and determine that the slope at the tangent line at x equals 4 is equal to 120. Looking at a second sample problem, let's define a new function g of x, which is equal to 1 over x squared. And the question is to find the derivative at x equals 3. Now you may remember that we have been doing the power rule solely on terms on the numerator, and you're correct. The power rule only works on terms in the numerator of a function, but as you remembered from a previous math class, 1 over x squared can be rewritten as x to the power of negative 2. And now we can perform the power rule as usual. So the derivative of g of x is equal to negative 2 times 1 times x to the power of negative 2 minus 1. And after simplification, this is equal to negative 2 times x to the power of negative 3. Generally, we don't like negative exponents as it's not great mathematical communication. So we'll just bring our x term back to the denominator, and we're left with negative 2 divided by x cubed. Lastly, we have to substitute x equals 3 into our derivative function to calculate the derivative at x equals 3, and after simplification, we get negative 2 over 27. To sum it up, we have learned that the power rule is a quicker method to calculate the derivative of a polynomial function. However, we can only use the power rule on terms that are in the numerator and on terms that have an x associated with them. So I'll leave you with the challenge problem that we'll take up in our next video. Calculate the derivative at x equals 2 of x plus 2 all of this squared. But for now, I hope you enjoyed this video and keep learning.